Okay, today we are going to continue the discussion on the convergence of a stability descent method. So recall that the stability descent method is to iterate like follows. So we suppose we are given the previous point, which is called xk. We want to compute the next one, which is xk plus 1, using this formula. Okay, so we focus on the case where the function f to be minimized is a quadratic function. So that means my f of x is 1/2 x transpose qx minus bx, b transpose x. So the q is a positive definite matrix, b is a vector, and our goal is to minimize this function f. Okay, so the stability descent method iterates in the following way, where the step size alpha k is determined by this formula, where this gk is the gradient of f at xk. Okay, so for each iteration, we have the xk, and we compute the gradient of f at this xk. That gives us the gk. And then we compute the alpha k, which is step size, using this formula. And then we get a scalar, and that's how we plug in the alpha k here. Then we'll get to the next iterate, which is xk plus 1. And then we repeat this procedure. Okay? So remember that for this algorithm to converge, if and only if this gamma k sums to infinity. So the series here is infinity. Recall the formula for the gamma k. Gamma k is completely determined by alpha k using this formula. This is one of the lemma that we showed before. And here, suppose we're using the stability descent method, and let's see if this gamma k is indeed summing to infinity. Okay, so now what we need to do is just plug in this alpha k into this formula. Okay, plug in this alpha k into this here, and see what happens. Okay, and see if this sum of gamma k is indeed infinity. Okay, so we just strictly forward plug this alpha k inside, and we'll realize that this alpha k is just this one here, right? And that is the same as this one here. So I basically just have 2 times this inside minus 1 times that. So that gives me just the alpha k for this whole parenthesis. Just 1 times this part. And similarly, this alpha k, when we plug this back in here, we can see what happens. So let's see. If I plug in this alpha k right here, I'll see that this denominator of alpha k is the same as the numerator here. So they should be cancelled, right, when I plug this alpha k in here. And also, as we said, in the parentheses, I will just have 1 times this. So we only have this left. So in total, what we have is, I'll have the gk transpose gk divided by gk transpose qgk. So let me just compute what happens here. So this is the alpha k that I write first. Okay, this is this term. And then I just repeat this term, which is gk transpose qgk divided by gk transpose q inverse gk. And in the big parenthesis, we said that it just reduce to the alpha k. Okay, and as we said earlier, this term, the denominator of the alpha k, and the numerator here will be cancelled because they're the same. Okay, so what's left is, so we cancel these two, and what's left is just this and this on the numerator. These two are the same, right? So it's just a square of this term. That is what we wrote here. And the denominator only has this and this to left. So that is this and this. Okay, so now we have reached to this step. And remember that the numerator here is the square of the inner product of G with itself. So within the square, this is just the squared norm of GK. And you have another square outside, so in total that will be just the fourth power of GK, the norm of GK, the fourth power of norm of GK. And on the denominator, we said that this part here is like the Q norm of GK. This part is the Q inverse norm of GK, or square the Q inverse norm of GK. Okay, so that this term becomes that, and this term becomes this. Okay, so that's what actually the gamma k is. And we just need to see that if this gamma k sums to infinity. Okay, we will take the sum of this gamma k for k from 1 to infinity, what happens? Okay, so a very easy way to show that this gamma k is infinity is to show that this number actually is bounded below by some constant independent of k. And by this, to show this, we need to use the Rayleigh's inequality we showed earlier. So remember that the Rayleigh's inequality we showed here is that for any vector x, this quantity is bounded between this ratio and this ratio. Okay, remember that on the left, first of all, on the right, that's the ratio of the largest eigenvalue of Q over the minimum eigenvalue of Q. Recall that this is called the condition number of Q, which is bigger than 1, and the larger this number is, the more you condition the Q is. That means the problem is in general more difficult to solve. Okay, and on the left-hand side, this is just the reciprocal of that. We have the minimum eigenvalue on the top and the maximum eigenvalue on the bottom. Okay, and this quantity is just bounded in between. So since this works for any vector G, any vector x, so we plug in x equal to the gk earlier. So say we replace xk with gk, and also these are replaced by the gk, we'll have exactly the formula we have here. So that's why it is bounded below by this quantity. Okay, so it's bounded below by this. But remember that Q is positive definite. So all the eigenvalues of Q are positive. That means this ratio, this fraction, has positive number on the numerator and also denominator. That's why it must be bounded away from 0. It's a positive number. Okay, so if each gamma k is greater than some constant like this, then you take the sum, then you will be infinity, right? If you take the sum of a gamma k, it will be infinity because every one of them is bounded away from 0. It's at least this large. Okay, so this shows that the gamma k actually goes to infinity if we choose the we choose to use the stabilization method, where the gamma k, alpha k is defined in this way. Okay, so actually, in general, if we have a gradient descent method that we want to use, say we don't want the stabilization method since it may require additional computation of this thing. Let's say we take the simplest way. We just do a gradient descent method with fixed step size or constant step size. So what that means is, suppose we're still trying to solve this problem, where this function f is quadratic and we do this gradient method with constant step size or fixed step size alpha. So what that means is we compute the xk plus 1 by xk minus alpha gk, where this gk is the gradient. So the gk, as before, is just the gradient of f at xk. Okay, and then for this particular case where the function f is quadratic, we know this is just qxk minus b. Okay, so let's see what if we apply this gradient descent method with a constant step size in this way. Then for this algorithm to converge, which means that for this xk to converge to the solution of this problem, what is the range of this alpha? So how should we choose the step size? Okay, so here the theorem says that if you are going to use this method with a constant step size, then this algorithm will converge if and only if this alpha is in this range. It's between 0 and 2 over the maximum eigenvalue of Q. Okay, so this is a sufficient and necessary condition for this algorithm to converge to the minimum of this minimizer of this objective function. Okay, so to prove this result, since this is a sufficient and necessary condition, we need to show first is sufficient, and next we show is necessary. So to show it is sufficient, suppose that we chose our step size alpha between this within this range, and let's see that this algorithm actually converges. Okay, so now first suppose that we chose this alpha in this range, and to show this algorithm converge, we just need to show that the corresponding gamma k sums to infinity. Okay, so let's take a look at the gamma k. So the gamma k, according to the formula before, is equal to this, where this step size alpha, since we choose this constant step size, so the alpha is a fixed constant. But if we choose this, then we realize that first of all, this numerator here is greater than or equal to the minimum eigenvalue. So it's greater than or equal to this. Right? This is because an earlier result that we have. So for any vector, the Q norm of this vector, square root Q norm of this vector is less than or equal to the maximum eigenvalue of Q times the square norm of X. Okay, so we're just replacing this X and this X by GK. Okay, so here, this means that this is greater than or equal to this. Sorry, I should say this side. So it's greater for any vector. So we plug in GK, the GK here. The square Q norm of GK will be greater than or equal to this quantity. So that's how we got the first inequality here. Got the first term here. And similarly, we can show that this is less than or equal to the maximum eigenvalue. For the same inequality, we can show that this is less than or equal to maximum eigenvalue of Q inverse times the square norm of GK. But we remember that the sorry, it should be maximum here. Should maximum here. Okay. So because the denominator, which is denominator is here, so because this is less than or equal to that, so if we put our reciprocal, if we put it on the denominator, this will be bigger than this, right? So that's why if we put it on the denominator, this will be bigger than 1 over this quantity here. Okay, so that's how we got the numerator is bigger than this, the denominator is smaller than this, so that's why we got this. Okay, that's one. The other one is that here, this quantity here is going to be greater than or equal to 1 over this. So the reason is similar. It's because the GK two norm, I should say, the square norm of square Q norm of GK is less than or equal to the the maximum eigenvalue of Q times the square norm of GK. So that's why if I divide both sides by this and this, what do I get is the GK square over GK Q norm squared. It's bigger than or equal to 1 over lambda max of Q. So that's how I get this quantity here is bigger than or equal to 1 over this. But I have an extra 2 here, so that's why I copied it here. Okay, so now I know that my gamma k is greater than or equal to this quantity. Now you see these two are cancelled, and there will be nothing dependent on k anymore. So we'll just have the alpha, which I copy here. I have the minimum eigenvalue, which I have 1 of this, and also the 1 over the maximum eigenvalue of Q inverse. This should be equal to the lambda mean of Q, right? This is the result we showed earlier. So that's why the two here together gives us the squared minimum eigenvalue of Q. And I'm just copying everything in the parentheses back in here. Okay, so now you can see, first of all, this number is bigger than 0, right? Because Q is positive definite. And then also the alpha needs to be, since we chose alpha to be between 0 and 2 over the maximum eigenvalue of Q, so that's why alpha is bigger than 0, and this minus alpha is also bigger than 0. So the two, all of them together is bigger than 0, and this is independent of k. So this is a fixed constant that is independent of k and is positive. So if every gamma k is bounded below by this positive number, and then taking the sum of gamma k will be infinity just like before, and that means this algorithm is convergent. Okay, so the gradient method with a constant step size alpha chosen in this interval, open interval, is guaranteed to converge for the quadratic function. So next, let's show the condition is also necessary. So to show the condition is necessary, we need to show that if the algorithm converges, then we must have this alpha in this range. Okay, let's prove it by contradiction. Suppose the method converges, but alpha is actually smaller than or equal to 0, or is bigger than or equal to this quantity. Suppose it's outside of the range, and let's see what could happen. So if this is the case, then let's say that we chose a initial value x0, and for the algorithm to converge, it must be convergent no matter which x0 you chose. So now here, to show that it's not convergent, I just need to show that for some x0, this method will not give us a convergent result. The sequence generated by this algorithm will not be convergent. And how we chose this special x0 that makes this algorithm fail is to choose it such that this x0 minus x star is the eigenvector corresponding to the largest eigenvalue of Q. Okay, so just say that we chose this x0 in this way, and we see that the algorithm will not converge. Okay, so if that's the case, if we chose this as the largest eigenvalue of Q, then that means if I apply A to x0 minus x star, this should be equal to the largest eigenvalue of Q, it should be Q here, times x0 minus x star. Okay, remember that this one here is a constant. Okay, it's a positive number. Okay, so let's proceed with this equation. So if we chose x0 in this way, then let's look at the arrow from the k+1th iterate of the algorithm to this x star. So this is the k+1th iterate of the algorithm. This x star is the minimizer. Okay, it's the minimizer of f. So according to the formula, how we got the xk plus 1, below here, how we got the xk plus 1, it's just this is just equal to this minus this. Okay, so these two are identical. And remember that the gk is gradient f at xk, and that is equal to this. So I replace the gk by that. And now also the minimizer of the quadratic function. We know the minimizer of the quadratic function should satisfy the gradient f, which is qx star equals to minus b equals to 0. So that means at the minimizer x star, the qx star should be equal to b. Right? So the b is actually equal to qx star. B equals to qx star. Okay, because x star is the minimizer. Okay, now things become easier. I have this xk and x star. And here I can extract the q. I'll just have this alpha q times xk minus x star. So I combine the two terms. I will have I plus alpha q times x star minus xk minus x star. So this is the vector. So this is the vector, and this is the matrix. Okay, so I got the relation between the arrow here and the previous arrow. So when I say arrow, this means the difference from my current iterate to x star to the solution. And this is next arrow. And they're related by multiplying this matrix. Okay, so if I do that, I can also take the same thing to this. This should be I minus alpha q times the previous arrow, which is xk minus 1 minus x star. Okay, so by doing this repeatedly, we'll have we can reduce this k one by one, and every time we reduce k by 1, we will have another I minus alpha q outside, multiply to it. So that's why when we keep reducing this is essentially just so alpha q square x k minus 1 x minus x star. And you can just keep doing that, then eventually we reach to this. Okay, so now remember that x0 was chosen such that this is the eigenvector of q, right? And if we have this as the eigenvector of q, then this whole thing is also eigenvector of I minus alpha q. Right? You'll know that if q of something, let's say qx equals to lambda x, then if I multiply any alpha times to the both sides, I will have this. Okay, and then I take a negative of both sides and I add x. So x minus alpha qx will be equal to x minus alpha lambda x. So on the left-hand side, this is just the identity minus alpha q times x. On the right-hand side, I will just have 1 minus alpha lambda, which is scalar, times x. So that means x is also an eigenvector of I minus alpha q, and the corresponding eigenvalue is 1 minus alpha lambda. Okay, so this applies here. So I know that this is true. So that also means that I minus alpha q times x0 minus x star will be also equal to 1 minus alpha lambda max of q times x0 minus x star, right? So that's what happens when I apply this for once. But once I apply it for once, if I apply the second time, apply it for k times, I will get this, right? Or k plus 1 times, I'll get this. The reason is, if you have x as an eigenvector of some matrix Q, So if qx equals to lambda x, say, then your q square x will be equal to the q times qx, and the qx is lambda x. It's just lambda x, and I can pull out the lambda, which is lambda of qx, and the qx itself, which is the lambda x, right? So this is just equal to lambda times lambda x. That's why I have just lambda square x. So similarly, you can just apply this for k plus 1 times, or k times, and you correspondingly get this many lambda outside. Okay, so that's the reason, exact reason here. So if I know that when I apply when I have applied the I minus alpha q for k plus 1 times to this eigenvector, then we have the corresponding eigenvalue for k plus 1 times this. Okay, so that's how we get from this to this. And now we're almost done. We want to check if our error from the x star, or distance from the x star, is actually decreasing. So remember that this is the error, right? So the norm of this will be the distance from xk plus 1 to x star. So let's take the norm on both sides. So I pick the norm. I'll have the norm here. But this is a scalar here. So I can pull it out, take an absolute value and pull it out. So to take the absolute value and pull it out, I get this. Okay, so the k plus 1's power of this norm, of this magnitude, and also the norm here. Right? When I take the norm of the whole thing, then this, I will just move it outside. Take the absolute value and move it outside. And here I have this. Okay, so let's see. On the right-hand side, I have this as the initial distance. Right? When I chose the x0, this is the initial distance from x star. And this is the distance after the k plus 1 iterations. Okay? After k iterations. Right? And then let's see if this is really reduced. Well, that depends on what's the number or what's the value of this quantity here. If we chose alpha less than equal to 0 or bigger than equal to this quantity, then we can see that this one in the inside will have a magnitude bigger than or equal to 1. The reason is, say, apparently if this alpha is chosen less than or equal to 0, this whole thing will be greater than equal to 0, right? Because lambda max of q is positive. If we chose alpha to be bigger than 2 over lambda max of q, then alpha times lambda q will be bigger than equal to 2, right? If we chose the alpha in this way, then I just multiply both sides by lambda of q. I'll get this. And then that means 1 minus alpha lambda max of q will be less than equal to 1 minus 2, which is equal to negative 1. So that means the value here will be less than equal to 1, less than equal to negative 1. So take the absolute value will be greater than equal to 1. And you take so in either case, the magnitude or the absolute value of this one is bigger than or equal to 1. You take the k plus 1th power is still greater than equal to 1. Okay? So that means we can never reduce this. Okay? Either we keep the same if this quantity is equal to 1, or we'll actually get larger and larger error if this quantity here is even bigger than 1. Okay? Because the k plus 1th power will just make this blow up. So we're not really reducing the distance. That means in this case, when our alpha is chosen in either of these two, from either of these two choices, the method will not converge. Okay, so that means our alpha has to be in the open interval from 0 to this. Okay, so this shows the necessity of this condition. So that means if I want this algorithm to converge, then this alpha must be chosen in this way. So now let's take a look at an example. So suppose we're given a quadratic function f that we want to minimize, and then we apply the gradient method with a fixed step size alpha, and then our question is, how do we find this alpha? What is the range of this alpha? Okay, so this quadratic function f is given in this way. And this is like the matrix A, this is like the vector B, and this constant doesn't really matter because you just shift your function value by this, but it doesn't affect the choice of your minimizer, right? If your minimizer, if your x can minimize this, then can also minimize this plus 24. It doesn't change. Okay, so the function value will change, but the minimizer will not change. Okay, and first we need to do is to convert this into the standard quadratic form, which means we need to add this matrix A with this transpose, and then we call this Q. Okay, so by doing that, we'll have the standard form. First of all, the Q will be just the A plus A transpose that becomes this. Okay, so if this is A, and the A plus A transpose becomes this. So that's my matrix Q here. And we have the Q and I have the 1/2 outside. So this is the equivalent, it's exactly the same function like this one. Okay, then we know that the Q, as we said, is just this. Okay, it's just A plus A transpose. We said that if we want the gradient method to converge with a gradient method with a constant step size to converge, then the step size alpha has to be chosen between 0 and 2 over the largest eigenvalue, lambda max of Q. Okay, so the Q is this, and then we just need to figure out what are the eigenvalues of Q, and choose the largest one. Okay, so to compute the eigenvalues of Q, take the determinant of this, and that's just this lambda I minus Q determinant, and then we can get a quadratic function of lambda because this Q is 2 by 2 matrix. So I have a quadratic function of lambda, is this, right? And then we simplify it into this form. So that means the solution is lambda equal to 6 or lambda equals to 12. So these are the two only roots of this quadratic function of lambda. So that means the smallest eigenvalue of Q is 6, and the largest one is 12. Okay. So according to the theorem we developed earlier, the step size alpha needs to be between 0 and 2 over 12, which is 1 over 6. So the conclusion we are making here is that if we're going to apply the gradient method with a fixed step size to this quadratic function to minimize this quadratic function, then our fixed step size alpha needs to be in this range. Okay. So before we move on, I actually want to before we move on, I want to make give you something that is a more general result comparable to the one given in the book. So remember that what we just showed is that if I'm trying to minimize this function fx and this fx, is a quadratic function, then the claim which is made is that for a algorithm, for a gradient descent method or gradient method with fixed step size, we know that is given by the xk plus 1 equals to xk minus alpha gk. for this algorithm to converge, if and only if the alpha needs to be chosen between 0 and 2 over the largest eigenvalue of Q. Okay, so this is really a special problem. As I said, this is just a quadratic function here. Okay, the question is, in practice, although quadratic function has many applications, it appears in lots of applications in the real world, but not, apparently not all the problem we are trying to solve is a quadratic function, right? Not all the objective functions we see in practice are quadratic functions. So what happens if it's not quadratic function? Can we still use this method? Can we still use this gradient descent method with a constant step size? And if it's not quadratic, how should we choose this step size? Okay, so here I'm going to give you a more general result. Okay, so general case. So I would just have this, just try to minimize this function fx, where f is not necessarily quadratic, just some general function. Okay? But I do need to make a assumption on this f. So f is not necessarily quadratic. Okay, but we do need to make an assumption here. So we'll assume that function f is differentiable. Okay, assuming that f is differentiable, so we can take a gradient at least. And the gradient f is L Lipschitz continuous. So I believe you all have seen what's the definition for Lipschitz continuity, which means for any x and y, the f of x, gradient f of x, minus gradient f of y, these are the gradients at x and y, so these are two vectors, is less than or equal to L times the norm of x minus y. So by L Lipschitz continuity, the L is some constant. The L Lipschitz continuity means that the gradient f satisfies this for any x and y. Okay, so this function value, difference of function values, remember that both are vectors, so I need to take the vector norm outside, is less than or equal to the L times the norm of the arguments. Okay, so this is the L. Okay, so for example, if this is 10, then you just need to have this as less than or equal to 10 times x minus 1 norm. Okay, so this is the only assumption that we make. And we're going to show that as long as we chose the alpha between the same as before, if we choose alpha between in this range, then the algorithm will converge. But notice that difference here is that we had a quadratic function here. So that's how we got this q, and that's how we compute this denominator here. But this is not a quadratic function anymore, as we said. It's not necessarily quadratic. So what does this mean? Okay, so this is actually the L here. So let me show you why that's the case. Say for example, if I have the fx defined as the quadratic function as before, then as we showed earlier, the gradient f is just a qx minus b, right? And now let's see the gradient f of x minus gradient f of y. What happens to this? It's just qx minus b minus another qy minus b. Right, when I plug in x and y separate respectively, I'll get this. And as you can see, the b's are cancelled. We'll just have the q times x minus q times y. So I put them together, I will have just have this. Okay, and you know that this is just bounded by the maximum eigenvalue of q times the norm of x minus y. Right? So that means the if f is a quadratic function like this, then actually we know that the gradient f, which is this, is Lipschitz. It's Lipschitz with this as the constant L. This is like the L, right? Compared to this one here, this has the same form, and this is just the L. Okay, so what we're going to prove is that in general, even if it's not the function f is not quadratic, we can still get a range like this, except that here the alpha needs to be between 0 and 2 over L, where L is a Lipschitz constant for the gradient of f. Okay, and a special case of what we're going to develop is this quadratic function. When the function is actually quadratic, then that's a special case of what we're going to prove. Okay, so let's see why for this general function f, the step size needs to be between 0 and 2 over L. Okay, so first I will need to prove a general result or a lemma to show this. Okay, so first a lemma. Okay, so suppose gradient f is L Lipschitz continuous. Then I can show that for any x and y, there is f of y is less than or equal to f of x plus f of gradient f of x. You know this is the vector, right? So it's a gradient of f at x. So it's a vector. I will multiply this with x minus y, y minus x. So both are vectors. So I'm taking the inner product of these two vectors, and then this. Okay, for any x and y, I will have this. Okay, so to prove this, I'm going to define for any y and x, we define this is very similar to what we did before. We define a line search function. It's a function of alpha and defined as f of x plus alpha times y minus x. Okay, so alpha is just scalar. Alpha is just the scalar. And when alpha, so what I'm having on this for this phi alpha is that, say this is the point x, this is the point y. For these two given points, I'm going to move along from x to y. And the function is defined in the whole space. The f is defined on the whole space. So if I restrict myself to this line segment, the function f is only taking the function value over this line segment. And these function values will be actually the function phi here. Okay, so as you can see, for fixed x and y, I can vary my alpha, and I will get different function values of phi. Especially when alpha equals to 0, I just need to plug in alpha equals to 0. I'll have this as f of x. And similarly, if I plug in alpha equals to 1, I'll have phi of 1 equals to, this is x plus 1 times y minus x, which gives me just y. So it's just the f of y. Okay? And moreover, we know that the phi prime of alpha, we just need to apply the chain rule to the phi of alpha. We'll get a gradient f of x plus alpha y minus x transpose times y minus x. Okay, so we just take the derivative with respect to alpha here, and we use the chain rule. So we have done this for multiple times so far. Okay, so I have this information now. What I'm going to do is, remember that this phi is just a univariate function, which means this is alpha, so maybe this is my phi, 0 to 1. This is my phi of alpha. Okay, just a univariate function. So for univariate function, I know that the phi 1 equals to phi 0 plus the integral of phi prime from 0 to 1. This is by the fundamental theorem of calculus, right? And then I also know that if I add this phi prime of alpha, d alpha, I can add this, I subtract it first, the phi prime of 0, d alpha, and add it back, phi prime of 0 at d alpha. Okay, so these are actually just two constants. The reason is this is a constant. You take the integral of a constant, it's just the length of this integral, which is 1 times this constant. So this is nothing but just a phi prime of 0. This is also phi prime of 0. So I'm going to move the last phi prime of 0 back to here. And then I'm going to combine the middle two terms. I'm going to combine these two, especially I'm just combining their integrand. That's giving me phi prime of alpha minus phi prime of 0 d alpha. Okay, so now I need to estimate the last integral. And I want to see what happens to the last integral. Okay, to recall that this phi prime of alpha minus phi prime of 0 is equal to, remember that this is phi alpha, phi 0 is just the same thing except the alpha is set to 0, right? So let's just copy things here. So that's my phi prime of alpha. And also I need the phi prime of 0. So I will not have anything other than x inside this, the y minus x. And apparently they both have this y minus x. So I just combine the gradient f. Okay, I have the transpose on each of them, but I can put them together first and then put the transpose. Okay, remember that both these are all vectors, right? This column vector, column vector. When we put a transpose, this becomes a row vector, and this is the column vector. Okay, so I have this. Then I can take an absolute value. So absolute value of the inner product of two vectors, according to the Cauchy-Schwarz inequality, this is less than or equal to the product of their individual norms. Okay. Okay, just like I have two vectors. I call A. Let me call it x and y. I know that the absolute value of this is less than or equal to the norm of x times the norm of y, right? This is called Cauchy-Schwarz inequality. Okay, so that's how we got this. And now you can realize that I have gradient f of something minus gradient f of another thing. Okay, gradient f has this, and then gradient f has this. We said that the gradient f is Lipschitz, so no matter what I plug in here, the norm of this gradient will be less than or equal to this. Sorry, here, the norm of the gradient will be less than or equal to this. Right? So that's why it should be just less than or equal to L times the norm of their difference. So difference of the arguments, the first argument is this. The second argument is x. And then I still have this outside. You can see inside here, this x is cancelled with this x. Right? So this will be cancelled, and then I'll have just the alpha times y minus x. But alpha is a scalar, so I can pull it out. Alpha is not just scalar, it's actually positive scalar. So my alpha here is between 0 and 1. Right? It's between 0 and 1. So this is actually a positive number. So this is actually equal to L times alpha times y minus x. And I have another y minus x. So instead of instead of multiply them together, I just have the square. Okay, that's what happens when I take a look at the absolute value of this integrand. I show that this quantity, the absolute value of the integrand, is actually bounded by that. And this means, so I have, if I take the integral of phi prime of alpha minus phi prime of 0 d alpha, I know that this is going to be less than or equal to the absolute value of the integrand. And according to our derivation here, the integrand is bounded by that. So this is less than or equal to 0 to 1 L alpha y minus x norm squared d alpha. But you remember that L is a constant. Y minus x squared is also independent of alpha. So I can pull them out. I have just this integral from 0 to 1 alpha d alpha. And then you know that this integral is just 1/2. Right? Here, this is just 1/2. So that's why in total I have just L over 2 y minus x squared. Okay, so now see what we have done. We prove that this absolute value of this is actually this one here, right? And this is bounded by that. So that means if I call this equation star, I show that this just becomes phi of 1 is less than or equal to phi of 0 plus phi prime of 0 plus half L times y minus x squared. But now I just need to plug in the phi of 1, phi of 0, and the phi prime of 0. But remember the phi 1 is this, phi 0 is this, the phi prime of 0 is just, plug in 0 here. Okay, so I will have f of y on the left, that is less than or equal to f of x, plus this, what we showed before is gradient f at x transpose times y minus x. And this is the claim we made. Right? So this shows that if gradient f is Lipschitz continuous, then we actually have this. Okay, so this is the key result we're going to use to prove that for general function f, the gradient method with constant step size can converge if the alpha step size alpha is between the range, between interval or within the interval 0 to 2 over L. Okay, so here is the final claim I'm going to make. Okay, so the proof is this. Now remember that the gradient method with the fixed step size is this, right? So just recall it. Okay, so this is the gradient method with step size alpha. Okay. So let's look at the f of k plus 1. Okay, let me actually leave this equation here. So let's say, because this holds for any x and y, so let's take y to be xk plus 1. I take x to be xk. Okay, so then by copying this formula, so this is my f of y, should be less than or equal to f of x, which is xk, plus gradient f at xk, transpose xk plus 1 minus xk plus half L xk minus xk plus 1 minus xk, right? So I'm just using this formula right here. I'll get this. So I have this. And now, just f of xk. In here, this is just the gk, right? This is just the gk. And then what is this? Xk plus 1 minus xk. So I know the relation here. So xk minus xk plus 1 minus xk will be just a negative gk. So what I have here is just a gk transpose times negative alpha gk. And similarly here, inside that, just negative alpha gk. Okay, so let me simplify things. I still have the alpha k here, and I have the minus alpha gk norm squared. And I will have, on the last term, I can pull out the alpha. So I have L alpha squared over 2, again gk squared. Okay. All right, I can combine the last two terms because they're both gk squared. So I minus alpha 1 minus L alpha over 2 gk squared. All right, so from this we know if I move this last term to the left and move the f of xk plus 1 to the right, we'll have alpha 1 minus L alpha over 2 gk squared less than equal to f of xk minus f of xk plus 1. Okay, so now you can see if we choose alpha to be between 0 and 2 over L, what happens? We will see that by choosing alpha in this interval, this quantity here is positive, right? You actually can see this is the quadratic function of alpha. Let me see, alpha 1 minus L alpha over 2, right? This is the quadratic function, and that is equal to, I extract L over 2, I'll have the alpha 2 over L minus alpha. And I know this is the quadratic function of alpha. If I draw it, it's the alpha. I will just have, when alpha equals 0, this is 0. When alpha equals to 2 over L, this is also 0. And this, the leading term is negative, so actually it should be this. Okay, so apparently if I choose, so this function is at this. So if I choose alpha to be within this open interval, this must be a positive number, right? Or this must be a positive number. Okay, so that means this must be, on the left-hand side, it must be greater than or equal to 0. Actually, if it's equal to 0, if and only if gk is equal to 0. Okay, so you know this. It must be greater than or equal to 0. Okay, so now apparently, as you can see, because this is greater than or equal to 0, that means this f of xk is bigger than or equal to f of xk plus 1. That means this method is decent, right? It's a decent method. The iterate we generated will continuously decreasing the function value. The function value is non-increasing. It's non-increasing. So another thing that we can use is, what if we take the sum of this k from 0 to, say, capital K? So I take the sum of the little k from 0 to capital K minus 1, say. Then on the left-hand side, I know this is just alpha 1 minus L alpha over 2. And the sum of k from 0 to capital K minus 1, gk. On the right-hand side, that's interesting. You can see that I will have, when k equals 0, this is f of x0 minus f of x1. And then for k equals to 1, I'll have f of x1 minus f of x2. So the f of x1 is cancelled with the previous negative f of x1. Right? So I just have f of x0 minus f of x1. Right? Let me erase those things. Have this plus f of x1. This is the case when little k equals to 1. Right? This is the second term. And all the way to the last one, which is f of x k minus 1 minus f of x capital K. Okay? And what I just said is this will be cancelled with this. And also this will be cancelled with the next coming f of x2. All the way to this one is also cancelled. The only thing left is the head and this tail. So that means just f of x0 minus f of x capital K. Okay? This is interesting because remember that xk is just what we got after k iterations. And whatever we get, it cannot be better. It cannot be smaller than the optimal function value, right? Because optimal function value is minimum. Because x star is a minimizer, then f of x star must be the minimum value we can get for f of x. Right? So that means this must be less than or equal to any x you plug into f. For example, we can plug into this. Okay, so because f of x star is less than or equal to that, so negative f of x star will be bigger. Negative of this will be bigger than or equal to negative of this. So that's why this one will be less than or equal to negative of f of x star. So this is just f of Okay, so let's see what we got. On the left-hand side, I have the sum of this times a positive constant. On the right-hand side, I have this, which is a fixed number. Since once I chose my initial x0, this one is fixed. So although I don't know what the vector is, since I don't really know what this one is. But I know this is a fixed number, right? So what I proved is the sum of this thing is always bounded by this up to some constant. Right? But the constant doesn't matter, it's a positive constant. Okay. Say on the left-hand side, because the sum of this GK, I have this is just the sum of GK for the first K terms. So they must be bigger than, so I keep the constant here. This term must be bigger than the K times the minimum value ever seen. Right? Because the sum of the K terms must be bigger than or equal to K times the minimum one of them. Right? So that's why this is less than or equal to alpha 1 minus L alpha over 2, and the sum of K from 0 to capital K minus 1, GK square. And this on the other side is less than or equal to f of x0 minus f of x star. Okay? So I just keep this on my left, at my left, and move this whole thing onto the right. So minimum value of GK square. This is less than or equal to f of x0 minus f of x star divided by, I put a constant at first, so it's alpha 1 minus L alpha over 2, and then K 1 over K. Okay, so this is very informative. The reason is, as we said, once we chose our alpha to be within our range, so the alpha is between 0 and 2 over L, I know that this is a positive constant. This is some positive number, right? Because this must be bigger than this, or bigger than equal to this, at least unless you choose. It's equal to 0 only if this is really optimal, right? It's already optimal. But this is a constant, positive constant. What I know is that if I run this algorithm, for K iterations, I run the gradient method with constant step size for K iterations. The minimum gradient I can see so far must be smaller than or equal to this, which is a constant times 1 over K. Okay, so if I want to see a small gradient, I just need to keep running, right? Because the minimum function value I would say must be decreasing. Minimum gradient, minimum value of this must be decreasing in the order of 1 over K. Okay? Say for K equals to 100, then this should 1 over 100, something like that. But it's going to 0. For K larger and larger, this goes to 0. For K greater, goes to infinity, right? So that's why we can see that the gradient we'll see is actually going to 0. At least the minimum one we'll see is greater than 0. Well, this is not as ideal as we hope. We really hope that the gradient of f at the xk, the last iterator we see is actually bounded. But for in general non-convex functions, this is the best we can get. We only show that this is bounded by that. But this is not a big issue. The reason is, remember that when we apply the gradient method, we generate this sequence. We get x. We start from x0, right? We compute the g0. This is what we got in the first iteration. And after that, we get x1, and we get g1, right? Then we move on to the next. For each one, after each iteration, we just check the function value. Let's say we check this. We check this value. If it's small, it's smaller than the previous one or the any one we got so far, we just record this xk. So for example, suppose at this iteration, at the first iteration we got x0 and g0, and we evaluate the g0. We keep the value g and x. And next iteration we get these values, and then we'll check the norm of g1. If the norm of g1 is smaller than the g0, we just replace the record we have by this G1 and the corresponding X1. If it's, the G1 norm is bigger than the G0 norm, so we do not replace it, we just keep it, keep the original record. So it's like that we have a memory here. Besides you running this algorithm, I also have a memory here that keeps tracking of the GK and XK. Well, actually, I have the GK norm as stored here. So once I have seen a new XK with a smaller GK, and then I will replace that. I'll replace the current one by the new one. Okay. Once I see, for example, next iteration, we see a GK plus 1 that is even smaller than this, I will just replace this GK XK by GK plus 1 XK plus 1, and also the norm there. And what this theorem says that after k iterations, the gradient you recorded must be less than or equal to 1 over k, or square of the gradient must be less than 1 over k times some constant, but that must be going to 0. Okay, so that means the algorithm is actually convergent, since our goal is to show that the GK goes to 0, or I want to find a point xk such that the gradient of f at xk, or this GK here, is close to 0. Okay, now we show that it's actually close to 0. It's getting closer and closer to 0. Although it's may never get to 0 exactly, but as long as the k iteration goes, then the gradient will be getting smaller and smaller. Okay, so that's going back to what we proved earlier. Recall that for this to hold, I just need this to be positive, and for that to be positive, I just need my alpha to be between 0 and the 2 over L. Okay, make this positive. So that's why at the beginning we said that if you choose this way, then this must be convergent. So this is a generalization of the very special case we considered in class, in the textbook, where it only applies to quadratic function.